So the last topic in the previous class, I want to recap, I want to remind you where I stopped. So I gave you the proof, or at least how the proof can be obtained. I did not write all the steps, but I showed you the roadmap how you can prove that this decomposition of the angular momentum of a rigid body can be done in terms of the inertia matrix of the RB at point A relative to a coordinate system which is shown here. So A, x1, x2, x3, it represents a Cartesian coordinate system which is having its origin at point A, and A is fixed to RB. Alright, so the first factor here is the inertia matrix, and the second factor is the column matrix representing the three scalar components of the angular velocity vector of this RB with respect to this frame. So if you follow the roadmap provided by me, you will be able to show that when you achieve such a decomposition, this inertia matrix or the so-called inertia matrix must have these 9 components. So it is a 3 by 3 matrix, and it is a symmetric matrix, and the components should be what I have written here on this side of the screen, right hand side of the screen. All these symbols represent integration over the body. Moving on, I want to remind you of this slide which I showed during our lecture number 19 and 20. I was talking about how to handle Euler's second axiom. Okay. Euler's second axiom is this: rate of change of angular momentum of a body with respect to an inertial reference frame must be equal to the net moment due to all external forces about that point 2. Well, I have it written here also. So the first thing, so how to handle Euler's axiom. I said 3 things we need to learn before we can start applying Euler's second axiom to various RBs. The first thing we looked at was the conversion of the Euler's second axiom to what we call as the modified Euler's second axiom. Right? So this is your ESA. Now ESA has this major restriction on itself that this point O that is appearing on the 2 sides of ESA, that point has to be fixed in I. And I said that in many problems this may be very inconvenient as far as dealing with the algebra is concerned, and that is why we want to relieve ourselves of this restriction. I wanted to be able to write of the modified form of Euler's second axiom where the angular momentum is computed about any point A, no restriction whatsoever. So left hand side I have rate of change of angular momentum about any point, and on the right hand side then we derived from ESA that right hand side will have MA which is the moment due to all external forces acting on the RB about point A. That's the first term. So there's a vector here. And then we realize that as we relieve ourselves of the restriction imposed on O and move to point A, you will also have to bring in an extra term, which is mass times RCA. You see this diagram? C is the center of mass of RB. RCA cross AAI, acceleration of this point A with respect to the inertial thread. So you do get freedom from O and you have a point of your choice, but as you do this, you should accommodate one more additional term in the equation. And indeed, this equation is called MESA. Alright, this is the first thing we learned. Then the second thing we learned, which we finished learning just in the last class, is being able to write the angular momentum of the RB about a point A which is fixed in M. Okay. In a different way. What do I mean by a different way? This is the original definition of angular momentum about point A with respect to a frame F. You have RPA, you have BPA, dm, integration over the whole body. What we learned that as long as A is fixed in M, you can write that HAF as a dot product between two quantities. First is the inertia matrix. Of RB at point A. Right, and omega mf is indeed the angular velocity of RB with respect to F. And the motivation with which we did this decomposition is this quantity depends only on mass distribution, not on motion. And whereas omega mf is, of course, kinematics, angular velocity of the RB. These two things we have completed. Now we are going to learn the third item, which we promised to ourselves that we will learn three things. We have now come to the stage that we have to go and learn the third item. What is the third item that we have to learn? The third item is choice of an appropriate coordinate system, working coordinate system, choice of an appropriate working coordinate system, so that the algebra of computing this quantity is minimized. Mind you, this is the LHS of MESA, right? It involves what? It involves not only the angular momentum, it involves rate of change in angular momentum, and that's why it is a more complicated quantity. Rate of change. Angular momentum with respect to I. Okay. How do we choose an appropriate coordinate system? Now when I say how to choose an appropriate coordinate system, these words themselves may not make it clear to you why computing this could be complicated and how choosing an appropriate coordinate system can address this. I understand that. So I'm going to explain it now. So let us consider the same body M, RBM. We have an inertial reference frame and I am and A is a point on RB. I am choosing a point A which is on the RB. Let this be center of mass, let this be A. Now so far we have learned that if A is a point on RB and if you have a Cartesian coordinate system which has its origin fixed to RB, right? If this is my working coordinate system, we have learned that HAI can be conveniently written in terms of the inertia matrix components and the angular velocity components. Now I am going to write this whole expression symbolically using sigma notation. And I hope that will make sense to you. Where is this coming from? This is coming from the same thing what I have shown many times in recent past. If you look at this matrix equation, right, and you have omega 1, omega 2, omega 3. I did show this expansion like 3-4 classes ago. The expansion is actually like this. Okay, you do the matrix multiplication IA1 with omega 1, IA1 2 with omega 2, IA1 3 with omega 3, and all these will be along E1. Similarly, you will have right. This will be the vector expression. This will also come directly from the derivation that I was trying to show towards the end of previous class. This vector HAI will turn out to be sum total of the 9 terms on the right hand side, where the first 3 terms are the coefficient of E1, the next 3 are coefficient of E2, and the next 3 are coefficient of E3. Three, one, one, 1, 1, 2. Okay. if you look at this, I can write this whole thing as I A j omega j E I, summation over I and j. So instead of filling 3 rows, 3 lines on my screen, I would rather like to use this compact expression and do some algebraic manipulation on this. This compact expression comes from here. I hope that is clear. Okay. So if I have this HAI expression where I am using this coordinate system as my working coordinate system, this is the expression. Now mind you, so far what condition I have put on my coordinate system. So this coordinate system, this C coordinate system is not fixed to I. Clearly it is not fixed to I, right? As the body moves with respect to I, A moves with I, A moves with the body, and thus A moves with respect to I. A is fixed to M. As the body moves, A also moves, and the origin of the coordinate system also moves as seen by this man here, and clearly it is not fixed to I. The next question is this coordinate system fixed to body M? Is this shown coordinate system fixed to body M? The answer is no, it is not fixed to body M either. Why is it not fixed? Because E1, E2, E3, I have not set anything on it, have no restriction. But A is fixed to body. So it's somewhat like a semi-fixed. Maybe I should use this word. This coordinate system is semi-fixed to the body. Semi-fixed to M. Origin is fixed, but I have not put any restriction on E1, E2, E3. Alright. That is the current situation as far as the coordinate system is concerned. Let us see what consequences it will have on the algebra when I try to differentiate this. HAI double summation IA ij omega j ei. Let's differentiate this whole this quantity with respect to frame I. Okay. What do we get? I get d dt I a I j with respect to I omega j e j. What else I get? I'm applying the product rule of differentiation here. D omega j dt I ej. sorry, EI it should be. Okay. I get one more term, which is three groups of terms, and the summation, double summation is there in all the terms. I have not written I1 to 3, J1 to 3 here, it is implied. Just trying to save some time here. The summation means going from I1 to 3 or J1 to 3. Two summations means one is for I, the other is for J. Three groups of terms we get here. Then I realize that Aij is after all a scalar. Omega j also is a scalar, and that is why I don't need to put I here and here, not required. Okay, so this vector is sum of I rate of change. When you're talking about rate of change, I is required only with the unit vectors of the Cartesian coordinate system I showed on the previous slide. Is the algebra complicated? Sure it is. Sure it is. You have a lot of terms here. There are 9 terms here. Another 9 terms here. Another 9 terms here. To get the rate of change of this, you have to track 27 terms. And that is why I have been spending so much time for last more than a week to learn things before I can do this algebra. So now with these 27 terms, I raise this question: can I put some more restrictions on this coordinate system, my working coordinate system, so that some terms, at least some terms, vanish automatically on the right hand side. This is item number 3 that we want to learn. What restriction I can put on the coordinate system? The restriction is that let us make the working coordinate system completely tied to the RB. Completely tied to the RB. Here I said it is semi-fixed to M. I am saying that now let us make it fully fixed to M. What will we achieve? What can we achieve? My claim is out of the 27 terms, 9 terms will vanish if I make the coordinate system completely tied to the RB. Let me show you. let us fix E1, E2, E3 axis to the RB. And once you do that, you will realize that this term here, which involves rate of change of IA, IJ, right? This term involves this quantity that will vanish. For all I equals 1, 2, 3, J equals 1, 2, 3. All 9 components will vanish. Mind you, I am not saying IA, IJ will vanish. No, I am not claiming that. I am saying that whatever IA, IJ is, it will not change with time. If AX1 is M fixed, this may require a little bit of imagination, visualization from your side. See, this RB at this time instant, it is oriented in this manner. Let me call it at time t. At time t plus delta t, the body may be oriented like this. But if I make this happen, then what will happen is that along with the body, the coordinate system will also change. Maybe I show it with a more regular shape that will be easier to visualize. At t equals 0, at t, and this is at t plus delta t. Okay, this is same frame I. At time t, the axes are oriented like this. Okay, this may be a point A. At time t plus delta t, as this man sees, the body has rotated. But if you allowed the body to take its coordinate system also with it itself, something like this. Okay, the IAIJ at time t will remain the same as IAIJ at time t plus delta t, if this condition is fulfilled. I hope it is making sense to you what I am saying. If you had not imposed this, then what would have happened? Even if you keep the origin fixed and you did not put the axis embedded in the body, what will happen? Even this will be the orientation of your working coordinate system. Parallel. Okay. So yellow color is showing if E1, E2, E3 not fixed to M, this will happen. And in this case, IA, IJ, T will not be the same as IA, IJ, T plus T. And this will imply that the rate of change of Ij will not be equal to 0. 27 terms you have to handle. I'm not going to do all that. I am going to do this and I am going to achieve this, and this will reduce the algebra from 27 to 18 terms, and I am willing to handle 18 terms. It is at least better than handling 27 terms. Okay. So coming back, handling Euler's second axiom, third term we have learned. Now we know. Third thing we have also learned. Lesson is fix the working coordinate system entirely to the body, its origin as well as the axis. As well as the unit vectors. Okay. There is any question, we will raise your hand, we will try to listen to you. It's a very important realization in this course. Now, having learned these three things, now we should feel more confidence that we can handle Euler's second axiom better. Now, Euler's second axiom or modified Euler's second axiom, both equations are vector equations, right? Both are vector equations. Inside they are equivalent. This vector equation is equivalent to three scalar equations. As usual, any vector equation will be equivalent to three scalar equations. So what I am going to do next is derive three different versions of the scalar equations that come out from modified Euler's second axiom. Why do I do this? Why don't I just start solving problems right away now that we have learned those three things? No, I want to derive these scalar versions because of some reasons. First is, those scalar equations will be excellent starting points to solve many dynamics problems because it will save time and effort. So every time when I am trying to solve a problem, I do not want to start from the vector form of the equation and then convert to scalar form and then solve those three scalar equations. Okay, there are two steps involved. Vector equation to three scalar equations and then solve three scalar equations. So in this procedure, the first part, which is conversion of a vector equation into three scalar equation, that I want to do right now, once and for all. Once I want to derive the three scalar equations and keep it handy whenever I am trying to solve a problem, rather than every time deriving the scalar equations first. That's what I mean by saving time and effort. Later, it will save time and effort for me. Also, these scalar equations are very convenient forms to build computer programs when you try to compute motion of RBs using a computer, right? In this course, we are not going to use any computer to predict the motion. In this course, we are going to use only pen and paper. However, in real life problem, one would like to write computer programs so that the computation part can be done by computer rather than we using a calculator. For example, when you launch a missile, and it is on its way towards a target, modern missiles do use onboard computer. Missiles have onboard computer which compute the dynamics of the kinematic and dynamic quantities involved in the motion, right? And you will write a computer program. Writing a computer program will be easier with these three scalar versions of MESA that I'm talking about, right? So with this motivation, let's work on this. And once we are done with that, we will be ready to solve some example problems. So there are three scalar versions I want to look at. Three scalar versions. So every vector equation has three scalar equations. So these three scalar equations I want to get, and I want to get those three scalar equations in three different versions. Alright, first version. The first version is applicable So in version 1 will be applicable if the following conditions are fulfilled. Number 1 is point A is a valid point. Valid point. What do I mean by a valid point? Recall MESA had this is the full form of MESA. A is called a valid point if is 0. And in that case, MESA will simplify further. Becomes just this much. The baggage, extra baggage is gone. A is a valid point. So version 1 will work if point A is a valid point. There are a few more conditions I want to put here, but before I do that, let's look at this valid point in a little bit more detail. So what are the conditions under which A will become a valid point? Case 1, when A will become a valid point, is that AAI is 0. Right? Then the extra baggage will be gone. Case 2 is when A is so maybe I put this AAI is 0 but VAI is not 0. This is one possibility. This can happen. A is a point, this is I, this is M. A is a point which may have some velocity, VAI not equal to 0, but VAI is not equal to 0, but this will be 0. Can happen. In that case, A is a valid point. Case 2, A is fixed to I, and in that case, even VAI will be 0 and AAI will also be 0. Both will be 0. That would be the situation when A is actually fixed in I. And this case takes us back to ESA. ESA. After all, ESA, what was the point about which angular momentum was computed in ESA? It was O fixed in I. That is the same as this situation when A is fixed in I. So of course MESA should be valid whenever ESA is valid. Right? So that is the second case. Third case, A is a valid point. What else can happen? A is C. The point A, which I wanted to take as this point A is actually the center of mass. A is equal to C. And if A is equal to C, and whether C is accelerating or not, C is moving or not with respect to I, nothing matters. As long as A is equal to C, the extra baggage term is gone. All your JEE problems you solved here. This form of MESA. You can go back and see every time you were applying anything like Euler's second axiom, you were working with center of mass. That's a special case when you get A to be a valid point. Case 4. RCA is parallel to AAI. Can happen. You choose point A such that this position vector of C from A, measured from A, is always parallel to the acceleration of A with respect to I. In that case also it will vanish. Okay. I can't think of any other case in which this extra baggage will be vanishing. So these are the situations in which A becomes a valid point. Coming back on the left side of the screen, I am trying to get scalar versions of MESA, and in this case I am saying that point A is a valid point. Okay, so of course this extra term is not going to appear. Second condition where version 1 will be applicable. I will derive that version, but I am putting the conditions up front. What is the second condition? The 3-axis of the working coordinate system comma x1 e1, x2 e2 and x3 e3 are the p-axis of the RB at point A. We know that already. And if you don't know it, you go and find out the p-axis. Once you know the p-axis, then you make those p-axis the 3-axis of your coordinate system. And then you will be able to apply version 1. Okay. The third condition is use A x1 e1, x2 e2, x3 e3 as your working coordinate system. I was prepared for this already. Nonetheless, I want to include it in the list. You first look for a point which is a valid point. You'll find the p-axis of the body at point A. Call them x1 e1, x2 e2, x3 e3. Construct a Cartesian coordinate system, this, and start using this as your working coordinate system. Okay. Under these conditions, now let's see what happens to MESA. Okay. So MESA now looks like this. Extra baggage term I have discarded because A is a valid point. I will write it and then I will strike it off. Gone. This is the body, point A here. Somehow we have found the p-axis. Found the p-axis. This is I. Our observer is sitting here. If this is my working coordinate system, what I have shown on the right hand side of the slide, of course, I can write MA, which is the net moment due to external force system acting on RB. I can write this vector without any problems. I should be able to express this as this. For that matter, any vector I should be able to write as 3 scalar components correspondingly multiplied by E1, E2, E3, and that gives you the vector. Okay, so these are scalar components of MA relative to our working coordinate system, which is this. Okay, the right hand side is really not a problem. It's just a matter of changing the symbol from vector MA to MA1, MA2 and MA3. Let's go to the left hand side. Left hand side is this. and I go back here, right? I said that in general d dt of HAI will have 27 terms. If I fix the coordinate system to the body, the yellow box term is gone and I'm left with two more summations, two more double summations, and those two double summations are actually accounting for 18 terms. So those 18 terms will be there. We'll take a break. After 2 minutes, let me complete this slide I want to write here. So this has first double summation IAIJ omega j dot EI plus another summation with IAIJ omega j DEI DTI. Can go back and check I have copied things properly. Right, double summation IAIJ d omega j dt, and this is, I am just writing that as, again saving some time and effort, I am writing it as omega j dot. We have used this notation earlier also, rate of change omega j dot. Mind you, this is a scalar. Okay, that's the first group of 9 terms. Second group of 9 terms, IAIJ omega j di dt with respect to I. So there a vector, rate of change of a vector is still involved, and I have to be careful with that. I should not drop this I. This I should be here. It has consequences. Rate of change of unit vector with respect to I, and then a dot here. Okay. I want to extract 3 scalar equations from it. It is still a vector equation. Extract 3 scalar equations, or extract 3 scalar equations. Yes, like that. And those 3 scalars I will match with MA1, MA2 and MA3. That will make it the version 1, first scalar version of MESA. We will continue. Let's take a break. Let's come back at 5:05.